Okay, hi everyone. In this lecture, we're going to talk about rings of fractions and localizations, and how do we construct local rings from standard rings that we're more familiar with. Okay, so first we need to talk about a process called localization. Okay, so let me give you a definition here. We're going to let A be an integral domain. And the first thing I need to tell you about is something called a multiplicative subset. A subset S in A is called multiplicative if two things happen. Okay, so the first thing is like a non-trivial or like a it eliminates trivialities. So the first condition just says that 0 is not in S and 1 is in S. Okay. The second condition says that S is closed under multiplication, and this is kind of the more important condition. Closed under multiplication. Okay. Now you can define these things in more general context. You don't have to have an integral domain to define multiplicative sets or localization, as you'll see, but um, it certainly makes it easier in the context of an integral domain. Okay. So given a multiplicative subset, there's pretty much one thing you want to do with this. We define something called the localization. It's denoted S inverse A, and it's essentially fractions with denominators in S. Okay. And we view this, in the case of an integral domain, we have a construction for a field of fractions, which I'll call frac A. And this localization we can just view as a subset of this field of fractions. Okay, here frac A is the field of fractions of our integral domain A. Okay, so given a multiplicative subset, I can define a collection S inverse A of fractions with denominators in S. Okay, so let's do an example of this. So, example, we're going to let A be an integral domain. Okay, there are two main important classes of multiplicative subsets. The first one is the multiplicative subset generated by an element. So we're going to let T be a non-zero element of A. Okay. We're going to define a multiplicative subset S sub T. This is essentially just powers of T. 1, T, T squared, and so on. So 1 is in here, 0 is not in here, assuming T is non-zero. And the product of two powers of T is another power of T. So this is certainly a multiplicative subset. And for the localization, we write a lower t for the localization. Okay, so these are fractions whose denominators are powers of t, or it can be written as whose like lowest form are denominators whose power of t is a power of t. Okay, so for part B, another important class. So if P subset of A is a prime ideal, turns out we can define S sub P to be A, kick out my prime ideal. This is a localization. Or, sorry, this is not a localization, but a multiplicative subset. So, let me quickly explain why that is. So, clearly, well, 1 is not in P because it's a proper ideal, so it is in S sub P. 0 is in P because it's an ideal, so that it's not in S sub P. And the condition that P is a prime ideal is exactly the condition that S sub P is closed under multiplication. Okay. So we write A sub P, A lower P, for S sub P inverse A. Okay, so you should think maybe A is the integers, P is maybe the ideal generated by 5. S sub P inverse A are fractions whose denominators are divisible by 5. Or, sorry, are fractions whose denominator is not divisible by 5. Yeah. Okay. Sorry. Important distinction there. Okay, so the next proposition tells us about what ideals look like in localizations. So, proposition let A be an integral domain S a multiplicative subset of A. Okay, and for an ideal A, we denote the ideal it generates in S inverse A by S inverse math frac A. So a small remark here. Given any localization, so given the localization S inverse capital A, I can view A as sitting inside this localization as fractions with denominator 1. That means that I can view this ideal as sitting inside that thing. And that's what I mean. The ideal it generates is take this set A viewed as sitting inside the localization and then generate the ideal there. Okay, and this proposition is going to tell us what S inverse A looks like. Okay. Then for an ideal A subset of S inverse A, we have S inverse math frac A intersect capital A. Okay. So essentially what this says is if I have an ideal in the localization, I can realize that as the localization of an ideal in A. Okay. And 2, it says if A is a prime ideal, in capital A, disjoint from S, then S inverse A intersect A equals A. Okay, so essentially what this is saying is, given an ideal in the localization, I can realize it as the localization of an ideal in A, and given a prime ideal in A disjoint from S, then I can realize it as the intersection of an ideal in the localization with A. Okay, so this is telling us there's some correspondence between ideals in my original ring A disjoint from S and those in the localization. Okay, so let's prove this proposition. Okay, so first let's prove 1. We're going to let, so mathfrak A is going to be an ideal in the localization. We're going to let A over S be an element here for A in big A and little s in S. We see little a is just A times A over S, and since this is an ideal, it's in mathfrak A, but it's also in big A because it's, from that statement right there. Okay. So what do we see? Thus, A over S, which is just 1 over S times A, is in S inverse mathfrak A intersect big A, so that we have one containment already done, so that A is certainly a subset of S inverse A intersect big A. Okay. To get the other direction, note that mathfrak A intersect A is always a subset of mathfrak A, and that mathfrak A, since this thing is an ideal, I can hit my intersection on the left with S inverse with denominators from S, and I'll still be in my ideal. Okay, thus 1 holds. Okay, so since A is an ideal and it contains this set A intersect big A, when I hit it with a 1 over S, I'm still going to be in mathfrak A. Okay, so next let's show 2. Okay, so we're going to let A subset of A be a prime ideal disjoint from S. And we're going to let little a be an A. What's our goal? Our goal is to show that it's in the intersection S inverse A and A. Well, this is like super, I would say this is clear because, well, we have, it's certainly in big A because mathfrak A is an ideal in A. and it's equal to little a over 1, which is in S inverse A. So we immediately see that S inverse mathfrak A intersect A as a subset here. Wait, sorry, I've flopped this. So we didn't even have to use the primeness or the disjointness from S to get the one containment that mathfrak A is contained in S inverse A intersect A. The concern is maybe this is bigger now. Wait, I'm somehow screwing this up. Okay, never mind. Sorry. So we're gonna now do the other direction. We're gonna let A be in S inverse A intersect A. Okay. Well, since A is in S inverse A, we can write this as some fraction A prime over S, where A prime is in A and S is in big S. Okay. So for an integral domain, this means that in terms of elements of A, we have S times A equals A prime. This is an equality taking place in my original ring A. So this is essentially what fractional equality means in the field of fractions of an integral domain. Now, here's a small remark. If A isn't an integral domain, you can do a lot of this stuff, but here is one instance where you need to be a little bit more careful. Yeah. So, since I have this equality of fractions here, I have this equality of elements in A, and thus we see, well, A prime is an element of the ideal mathfrak A. S times A is in here. Since this is a prime ideal and it's disjoint from S, since A is prime, we either have to know either A is in here or S is in here. But A is disjoint from S. So that's this. The latter condition can never happen. Thus, A is in. What did I want to say? Somehow this seems not right. Oh, okay, no, sorry. Yeah, this is fine. I got confused. I was looking at this up here and thinking that we already knew this, but we're actually, maybe I should have started a new paragraph right here. This A is somehow different than this A. Okay. So what is my ultimate goal? Well, my ultimate goal was to show that an element here wasn't here, and that's exactly what I just did. Thus, S inverse mathfrak A intersect A is contained in mathfrak A, and we've shown both directions of the equality, so that too holds. Okay, so what is the... So essentially, I guess maybe just to say a remark about the proof here. The proof is essentially carefully using the definitions. Part 1 is really not too bad. Part 2, you have to be a little bit more careful and use the primality of A and the disjointness from S. And you also you subtly or not use the fact that you're working in an integral domain, so that equality of fractions here really does mean equality of this product and this element here. Okay. So what is the point of the proposition? Point of the proposition is really the following result. Okay. This is the importance of the above proposition. So maybe corollary. I should give myself a little proof box. So the corollary, we're going to let A be an integral domain. And we're going to let S be a multiplicative subset. Then the map, okay, P maps to S inverse P, is a bijection between prime ideals of A disjoint from S and prime ideals of the localization. Of S inverse A. And the inverse of this map, the inverse is P maps to P intersect A. Okay, so what is this telling us? This is telling us essentially what, so the question this is answering is, what are the prime ideals of S inverse A? And the answer is exactly, it's the localization of prime ideals in A which are disjoint from S. Okay. And what do I want to say here? So the proof, I'm not going to go through the details of the proof. It essentially is just use the above proposition carefully. Proof. So maybe there's another exercise. Use the above proposition carefully. To show these two maps are well defined. Well defined and actually inverse to one another as claimed. Okay. So another way to think about this is you should think of this as some analog of, I guess some people call it the fourth isomorphism theorem, which tells you about ideals in a quotient ring. So prime ideals in a quotient ring are exactly prime ideals in the larger ring containing the ideal you're quotienting out by. And here, the condition, instead of containing the ideal you're quotienting out by, here the condition is being disjoint from your multiplicative set. And one last remark I want to make. So maybe you ask, like, okay, why is this called localization? Okay, And I'm not going to answer it fully, but I'll at least tell you what relation it has to the previous sections on local rings. Um, if P subset of A is a prime ideal, then the localization A localized at P. Remember, this means take A, kick out P, invert that, multiply it by A, is a local ring with unique maximal ideal. What do I want to call it? I guess I'll call it A, kick out P, inverse P. Okay. So you can check this. Maybe it's a good exercise to see what this looks like for the integers or something. Maybe P equals 5. Yeah. So this is one reason. Well, I guess if you've come to terms with the fact that local rings are called local rings, then this is one reason why localization is called localization, is because it gives you local rings in a very common scenario. Okay, and I guess again the real reason we keep using this word local stems from algebraic geometry, but this isn't. Yeah, this isn't particularly a lecture on algebraic geometry. Maybe someday it will be. Okay, that's all I want to say for this lecture.